discussing the concept of linear combination of vectors. Linear combination, as most of you must be knowing the concept of linear combination, the usual definition follows in case of vectors also. So first of all, we shall discuss the meaning of linear combination of vectors, followed by some of the important properties and like fundamental theorem and the fundamental theorem in space in context of vectors. We shall also discuss the condition of coplanarity as well as the collinearity of vectors, followed by some of the questions. So let's begin. Okay, so we have now another important as well as an interesting concept, that is linear combinations. Given a set of vectors A, B, C, then the vector R is equal to xa plus yb plus zc so on is called a linear combination of vectors A, B, C for any x, y, z belongs to R. This is in fact the general definition of linear combinations also, that you have certain number of scalars and if you take the term of the form R, in case of like here we have vectors A, B, C, then the vector R defined as xa plus yb plus zc plus so on is termed to be a linear combination of the vectors A, B and C where x, y, z belongs to R, that is they are real numbers. So in case of linear combination we again have some results which are if A and B are non-zero, if A and B are non-zero non-collinear vectors, then xa plus yb is equal to x dash a plus y dash b would imply x is x dash and y is y dash. If A and B are given to be non-zero non-collinear vectors satisfying this condition, then you can deduce that x would be equal to x dash and y would be equal to y dash. Then we have the fundamental theorem which says let A and B be non-zero non-collinear vectors. Then any vector R coplanar with A and B can be expressed uniquely as linear combination of A and B. That is, there exists some unique x and y belong to R such that xa plus yb would be equal to R. That just means suppose we are given two non-zero non-collinear vectors A and B, then if we have another vector R coplanar with A and B, then in that case that R can be represented as a linear combination of A and B. That is, we can write R as xa plus yb where x and y are some unique scalars, real numbers. Moreover, if A, B, C are non-zero, non-coplanar vectors, then xa plus yb plus zc equal to x dash a plus y dash b plus z dash c would imply x equal to x dash, y equal to y dash and z equal to x z dash. That is, the coefficients of the vector A would be same, of those of B would be same, and similarly those of C would be same. Next we have is the fundamental theorem in space. So let A, B and C be non-zero non-coplanar vectors in space. Then any vector R can be uniquely expressed as linear combination of A, B, C. This is in fact on the same lines as we have discussed just now. There will exist some unique scalars or unique real numbers x, y and z such that xa plus yb plus zc would be equal to the vector R. Next point that we have, next property that we have is if x1, x2, xn, this is if x1, x2, xn are n non-zero vectors and k1, k2, kn are n scalars, and if the linear combination k1, x1 plus k2, x2 plus kn, xn is equal to 0 implies all k1, k2, ki, that is all ki's or k1, k2, kn or each one of them is equal to 0, then we say that vectors x1, x2, xn are linearly independent vectors. So this is in fact again the general definition of linear independence. The vectors, if we have certain number of vectors, non-zero obviously, there are n non-zero vectors x1, x2, xn, and suppose we have got n number of scalars also k1, k2, kn such that the linear combination equal to 0, k1, x1 plus k2, x2 plus kn, xn is equal to 0 would imply, or it is implying that k1, k2, kn each one of them is 0, then we'll say that the vectors are linearly independent vectors. And similarly, we have if x1, x2, xn are not linearly independent, then they are said to be linearly dependent vectors. But obvious, if they are not linearly independent, that means they are linearly dependent. And in that case, if we have a term of the form k1 x1 plus k2 x2 plus, this will be plus kn xn equal to 0, and if there exists at least one kr non-zero, then x1, x2, xn are said to be linearly dependent. So if x1, x2, xn are either they can be linearly independent or dependent. In case they are dependent, that means we will have at least one ki which would be non-zero, and this sum is 0. k1 x1 plus k2 x2 plus kn xn is 0, while at least one ki would be non-zero. Then they will be termed as linearly dependent. Okay, now we have collinearity and coplanarity of points. The necessary and sufficient condition for 3 points with position vectors A, B and C to be collinear is that there exist scalars x, y, z not all 0 such that xa plus yb plus zc is 0 vector. So this is the necessary and sufficient condition for 3 points or 3 vectors to be collinear, that there will exist some constants x, y, z not all 0 such that xa plus yb plus zc would be equal to 0. Again, the necessary and sufficient condition for 4 points with position vectors a, b, c and d to be coplanar is that there exist scalars x, y, z and u not all 0 such that xa plus yb plus zc plus ud would be equal to 0. Just remember these two conditions as they will be utilized in questions. We shall also solve just now certain questions based on these concepts. So then the concepts would be much clearer. The first question that we have is, show that the vectors 5a plus 6b plus 7c, 7a minus 8b plus 9c and 3a plus 20b plus 5c are coplanar, where a, b, c are 3 non-coplanar vectors. Okay, first of all, I'll assume my a to be 5a plus 6b plus 7c. This is given. A is this. Let me assume a to be this. Then I have b is 7a minus 8b plus 9c and c is 3a plus 20b plus 5c. Now it's given a, b, c are coplanar. Show that the vectors are coplanar. Okay, we need to show. Okay, we are required to show that these three are coplanar. A, B, C are coplanar would imply that XA plus YB plus ZC equal to 0 must have a real solution, must have this xa plus yb plus zc equal to 0 must have a real solution for x, y, z other than the trivial solution, that is other than 0, 0, 0 triplet, right? We are required to prove that these vectors, that is a, b, c are coplanar. For that, we need to prove that xa plus yb plus zc equal to 0. This equation must have a real solution for x, y, z other than the trivial solution. Now, xa is x5a plus 6b plus 7c plus yb would be y7a minus 8b plus 9c plus z3a plus 20b plus 5c equal to 0. We begin with this equation, and if I collect the terms of vector A, I will get 5x plus 7y plus 3z. So I have 5x plus 7y plus 3z into vector A, plus again I will collect the terms of vector B, which would be 6x minus 8y
plus 20z. Let's see, 6x minus 8y plus 20z. Then for C I'll get 7x plus 9y plus 5z. So plus 7x plus 9y plus 5z into vector C would be equal to 0. Now this just means that the coefficients are 0 individually. So we have 5x plus 7y plus 3z is equal to 0. Then I'll have 6x minus 8y plus 20z would be equal to 0. Then I'll have 7x plus 9y plus 5z would be equal to 0. And now D is equal to, if you find out the determinant, I get 5, 7, 3, 6 minus 8, 20. This is minus 8. Then I have 7, 9, 5. This is the determinant that I have. So this would be equal to, let's calculate, minus 40 minus 180. This is 5 into minus 40 minus 180 minus 7, and I have 30 minus 140 plus 3 into 54 plus 56. If you solve out this, you will get it as 0. So what does that mean? We are getting the determinant as 0. So the three linear simultaneous equations, these three linear simultaneous equations we are talking about. So the three linear simultaneous equations in x, y, z have a non-trivial solution. So these three linear equations will have a non-trivial solution, and if they have a non-trivial solution, that means the vectors A, B and C are coplanar vectors. Because we began with this only, we were required to prove that they would have a non-trivial solution, and hence since we have already proved that, that means that these vectors capital A, capital B, capital C are coplanar vectors. Now the next question that we have is, if the vectors ai plus j plus k, I plus bj plus k and I plus j plus ck, where a, b and c are not equal to 1, are coplanar, then the value of this is, okay. So we are required to find out the value of this if we are given the condition that these three are coplanar. The given vectors are coplanar if, now the given vectors are coplanar if I find out the determinant of these coefficient, I get it as 1b1 1 1c is equal to 0, right? This is a1 1 1b1 and 1 1c. If this is equal to 0, which means just solve out this. So we have bc minus 1, then I have minus of 1 into c minus 1, then I have plus of 1 into 1 minus b would be equal to 0, right? So this gives me abc minus a minus c plus 1 minus b is equal to 0. So this gives me abc minus of a plus b plus c plus 2 would be equal to 0. This is one condition that I have obtained. Now what I will do is I will take up the term which we are required to evaluate. So we have 1 by 1 minus a plus 1 by 1 minus b plus 1 by 1 minus c. That would be equal to, we can find out, you can just take the LCM and I can write it in the form of summation of 1 minus b 1 minus c by 1 minus a 1 minus b 1 minus c, right? This is what I have obtained. I will try to further simplify this term. Now the numerator, if I take, numerator was equal to summation of 1 minus b plus c plus bc, right? 1 minus b plus c plus 1 minus b plus c plus bc. So if I open up this summation, that will be equal to 3 minus, we'll get twice of a plus b plus c, because you'll get b plus c then c plus a plus a plus b. So ultimately we have twice of a plus b plus c plus bc plus ca plus ab, right? And denominator is equal to, okay, so denominator, we have the denominator as 1 minus a plus b plus c plus ab plus bc plus ca minus we'll have abc, right? Okay, so this can be written as 1 minus a plus b plus c plus this also remains as it is. What about ABC? You can see we have obtained ABC as minus, ABC is equal to a plus b plus c minus 2, right? So we can utilize that value and we get ABC would be equal to a plus b plus c plus 2. So this gives me 3 minus twice of a plus b plus c plus ab plus bc plus ca. So the required value, that is 1 by 1 minus a plus 1 by 1 minus b plus 1 by 1 minus c would be equal to 3 minus twice, this is the numerator, this is the denominator that we have obtained, so we'll just divide both. So we have 3 minus twice of a plus b plus c plus ab plus bc plus ca divided by, denominator is 3 minus twice of a plus b plus c plus ab plus bc plus ca, and ultimately these two cancel out, and so we have the required value as 1. The answer of this term, that is the value of this term, is 1. So the concept of linear combination is quite simple. In fact, it is similar as we have already done. You people must have read already the general concept of linear combination. For vectors also the same conditions apply. And then we discuss linear independence and linear dependence. So the questions are also quite simple when they are asked on this concept, but do practice a good number of questions in order to develop a very good speed.
So I hope you must have understood the concept of linear combination. It is a simple concept as well as quite interesting. So yes, it can fetch you some easy scores. Just demands a good amount of practice. So do practice a good number of questions on it. Now in the next session we'll be switching to the applications of vectors in geometry, and again it does demand a good amount of practice because it is full of various formulae. So just stay tuned.